In this chapter, we're going to talk about a concept that's called momentum. To illustrate momentum, you know that, for example, it's harder to stop a truck than it is a small car when they're both moving at the same speed. And that's because the truck has a greater momentum. Well, how do we define exactly what momentum is? Momentum is the product of mass times velocity, or as you'll often see the formula, momentum is defined as m times v. Now, a very closely related concept is that of impulse. And impulse is defined as the product of force times time, F times t. And when you apply an impulse to an object, it causes a change in momentum. Well, if you think about it, that makes perfect sense, because what we've learned so far about Newton's second law is that when you apply a force on an object, the object accelerates. And the longer you apply that force, the greater the velocity that the object is ultimately going to attain, assuming that the force is in the same direction as the motion. And if the velocity is increasing, then that's going to mean that the object actually increases in momentum. So they're actually numerically equal to each other. The force, product of force times time, is actually equal to the change in momentum. So just a short example there. If you apply, for example, a 2 Newton force on an object for, let's say, 1 second, then 2 times 1, that's an impulse of 2 Newton seconds, and that would cause the object's momentum to also increase by 2 kilogram meters per second. Okay, lots of interesting applications of this impulse momentum. Many instances, like in sports, for example, you want to try to increase the momentum of an object. Let's take baseball, for example. So you have the batter, he hits the baseball with the bat, and he wants to try to hit the baseball as far as possible. So in other words, he wants to try to give the baseball the most momentum possible. Well, according to the impulse momentum equation, the product of force times time equals delta mv. So he applies the force on the baseball with the bat, but also he wants to make sure that that time that the bat and the ball are in contact is at a maximum. Now, when I was first learning how to swing a baseball bat, my father always used to tell me to follow through. And when you follow through, you are making sure that the contact time between the bat and the ball is as great as possible. That T factor there is as big as possible. And in doing that, you're going to apply the biggest change in momentum to the baseball. The same argument goes with bowling. When you're trying to throw the ball down the alley as fast as possible, you want to, again, follow through to make sure that your contact time between the hand and the bowling ball is maximum. Slap shot in hockey, same principle. All right, now let's look at the other side of the coin. Some instances, momentum is going to be decreased. So let's say that you're driving along in your car 60 miles per hour, and the car crashes, it comes to an immediate stop. Well, the car is experiencing a change in momentum, and so what does that is a force on the car, product of force times time. So if you take the car and you drive it into a bale of hay, for example, then the time that the bale of hay is in contact with the car is relatively long. And so therefore the force on the car is not going to be that great. On the other hand, if you hit a tree, then the contact time is real short, and the force is going to be extremely large, which will likely cause a lot of damage to the car. Same argument applies to the occupants of the car. They're traveling along at 60 miles an hour as well, And if they come to an immediate stop and an airbag deploys, well, then they tend to sink into the airbag and the time is extended, making the force much, much less. On the other hand, if there's no airbag and they just hit the steering wheel, then the time is really short and the force on their body is really large. Okay, a couple of other examples. Let's take a boxer, two boxers engaged in a bout, and one boxer throws a punch at the other, and he hits it, he lands. Now, if the boxer who gets hit, if his face is moving away from the punch, same argument, the contact time is going to be much larger, and so the force is going to be less. On the other hand, if the boxer's face is moving toward the second boxer who's throwing the punch, then the contact time is likely to be a lot less, and so the force is going to be much greater. Bouncing, even bigger effect. Let's say that you're standing under a window and there's a flower pot on the window, and the flower pot gets knocked off and it hits you on the head, comes down, hits you on the head, and it bounces back up. Well, that's kind of a double whammy, so to speak, because the contact time is going to be short, number one, but since the flower pot is bouncing up, it's not coming to a rest. It's actually changing direction and starting to go upward a little bit. And so that change in momentum is even bigger than it would be if the flower pot just came to rest. And so as a result, the force is much larger. Interestingly, people who break bricks using karate use that same principle. They take their hands and they apply the biggest force they possibly can, but they try to minimize the contact time, number one. And number two, they try to get their hand so that it bounces back up off the bricks so that this time ends up, the change in momentum of their hand is much greater. And so as a result, the force here is much bigger, hopefully enough to break the bricks. Now, a very important thing about momentum is that it is a conserved quantity. In other words, there's a very important principle here, the conservation of momentum. Okay, what does that mean? I'm going to jump down to the second bullet here. The total momentum of a closed system must be constant. What I mean by a closed system, there's no outside impulse on the objects. So if it's a closed system, the total momentum has to be constant. Okay, now, to understand this totally, you have to realize that momentum is, again, a vector quantity. Okay, hopefully we all know what this means now. Momentum has both magnitude and direction, and when we combine momentums, we have to make sure to combine them using vector addition that we learned about a few chapters ago. Okay, now, collisions are a very common application of this conservation momentum. So if you have, for example, two objects, let's say two spheres approaching each other, the total momentum before the collision must be equal to the total momentum after the collision. That's the conservation of momentum, again, assuming that there are no outside impulses on the objects. Now, we can classify collisions as being elastic, first of all. And in an elastic collision, might be a good approximation of an elastic collision might be when you have two pool balls, for example, colliding with each other. Okay, when they collide, there is very minimum amount of deformation of the surfaces. In other words, the pool balls don't noticeably squash, they don't deform at all. They do make a little bit of noise, and that means that the collision is not perfectly elastic. So, for example, you know that when two pool balls collide, there's like a little clicking sound. So that means there is some energy that is lost. We'll talk about energy more in the next section here. But a totally elastic collision would be that if there were no energy lost at all. As a matter of fact, we do a lab on our campus physics where we have two cars that collide and they have magnetic bumpers. And so when the two cars approach each other, they never even make contact. So there's obviously no deformation there, and there's actually no noise because there's never any contact between the two cars. It's just the magnetic fields that are repelling the two cars that's causing them to rebound. So that's a pretty good example of an elastic collision. Now, on the other hand, we have inelastic collisions, and in inelastic collisions, there is usually deformation of the surfaces. Oh, a good example of this might be if you take a piece of clay, like a clay ball, and you just drop it to the floor, it splats, the clay ball flattens out on one end, and it just sticks there. So in inelastic collision, number one, there is this deformation of the surface. The surfaces end up being deformed somewhat. And typically also the objects actually stick together. For example, the ball doesn't bound up off the floor. The piece of clay doesn't bound up off the floor. It just sticks there. Now, the important thing is that conservation of momentum applies equally to both of these situations. Both elastic collisions and inelastic collisions, conservation of momentum applies. All right, here is a pretty simple numerical example of the conservation of momentum. Let's say that you had a 1,000 kilogram train and it's moving at 10 meters per second. It collides and couples together with another 1,000 kilogram train, which is at rest. The question is, what is their combined velocity after they collide? Okay, so the way you would approach this problem is you would start off by calculating the total momentum before the two trains collided. So, first train has got 1,000 kilogram mass multiplied by its velocity, 10 meters per second. That gives it a momentum of 10,000 kilogram meters per second. Then we look at the other train, but the other train, which also had a mass of 1,000 kilograms, but it was at rest. So its velocity was zero, so it doesn't contribute anything to the total momentum. So the total momentum before the two trains collide was this 10,000 kilogram meters per second. Now, the conservation of momentum says, therefore, that means that the total momentum after they collide must also be 10,000 kilogram meters per second. Okay, well, now find out their velocity. If momentum is 10,000 kilogram meters per second equals m times v, their combined mass is 2,000 kilograms, so that's m. If we solve for v, then we would divide the 10,000 kilogram meters per second by the 2,000 kilograms and come up with a velocity of 5 meters per second. By the way, this is a good example of an inelastic collision because the two trains collide and they stick together.